Hey, Doug here. Did you know that 50% of marriages end in divorce? This couple or pair splits up, just like the electron when it gets excited. Now, today we're here to talk about electron pulse resonance or electron spin resonance. But what is that? What is EPR or ESR? For that, we can talk about the Jablonski diagram.
The Jablonski diagram shows the different electronic, vibrational, and rotational excited states of an electron. When an electron absorbs a photon, the electron can excite to one of the excited states based on the energy of the photon. When exciting electronically, the electron typically has some vibrational excitation as well, which is relaxed through vibrational relaxation to the ground vibrational state. While in an electronic excited state, the electron can go through intersystem crossing to enter the triplet state, where the vibrational excited state of the triplet state and the ground vibrational excited state have similar energies. An electron in the triplet state returns to the ground state in the form of a radiative decay called phosphorescence. This phosphorescence is much longer than fluorescence. In this experiment, we are analyzing the decay of the triplet state in naphthalene. However, the degeneracy of the triplet state makes analysis harder. So, the Zeeman splitting effect is used to break the degeneracy of the triplet state. The Zeeman splitting effect occurs when a magnetic field is applied to an electron, causing the degeneracy of the electron to fall away. This is due to the spin of the electron being parallel, which has a lower energy, or antiparallel, which has a higher energy, to the magnetic field. The equation for determining the splitting is the Bohr magneton mu b, the spectroscopic splitting factor G, and the magnetic field strength H multiplied together. The energy of each spin is the same variables multiplied by the spin of the electron, S sub z. As mentioned, this experiment is looking at the rate of decay of the triplet state of deuterated naphthalene, which is shown at the bottom right, and naphthalene, which is shown at the top right, and comparing them. This is done using ESR/EPR and only gives a signal where there is one unpaired electron, which occurs in the triplet state, which is why we are using the triplet state. And the field sweep spectra is given as the first derivative of the field sweep spectra. To determine the rate of the decay of the triplet state, kinetics must be used. Since the reaction involves only one molecule, since triplet state decay occurs within the molecule, the reaction is first order. This results in the equation for the change in concentration over time being equals to negative K1 times the concentration of the molecule in the triplet state. You can use calculus to determine the concentration at any given time based on the initial concentration, which gives an equation that looks like this, where it's the initial concentration times the exponent, or e to the negative rate times t. This also relates to Beer's law and allows you to substitute intensity for concentration. For this experiment, we had two hypotheses. First, the lifetime of the triplet state of the deuterated naphthalene would be longer than the protonated naphthalene due to the heavy atom effect increasing the lifetime of the triplet state. And second, the intensity of the protonated naphthalene will be much lower than the deuterated naphthalene due to the heavy atom effect increasing intensity of phosphorescence. The experiment was done by creating two solutions, one containing about 0.1 gram of deuterated naphthalene and the other containing about 0.1 gram of naphthalene, both dissolved in 2-methyl tetrahydrofuran. These solutions were pipetted into EPR2, which you see has the green tip over here, then placed into the Dewar finger, which is this thing that has the towel over it, and liquid nitrogen was poured into it. A lock switch was done, and the arc lamp shutter was turned to let light through. A field sweep scan was taken to determine the field strength that would give the best intensity, which is the maximum of this field sweep scan. And then a temporal kinetic scan was done to monitor how the triplet state decays over time. These two sweeps gave us two spectra, the field sweep spectra, which, as I've shown, and the time sweep spectra, which is shown on the next slide. The time sweep spectra shows how the intensity changes over time. So for deuterated naphthalene, we obtained this spectra, which shows an exponential decay of the intensity. It's very easy and nice to read. The spectra obtained for naphthalene looks like this. That doesn't look very good. So let's try that again. Okay, I have an idea. What I'm actually doing is a data smoothing technique using a Savitsky-Golay filter. This filter fits a low-degree polynomial to the data by a method of linearly squares and outputs where the polynomial has an inflection point. The graphic shown on the right shows you exactly what I mean by this. This increases precision and readability of the data without decreasing the tendency of the data too much. This is important since the tendency of the data allows us to tell what trend is going on. And the precision of the data allows us to make sure that the values are staying same to the original. So what does the decay look like after that? Well, it looks like this. Still not great, but you can see the decay of the triplet state slightly. For analysis, we want to ignore the part where the change in intensity is pretty constant. So here at the beginning and kind of here at the end. Since that is before the triplet state started to decay or after the triplet state has decayed. The mathematics behind determining the rate constants is by plotting the natural log of the intensity versus the time, which would result in the slope of the trend line being equal to the negative rate constant. Another value we looked at was the half-life of the triplet state, which occurs when the ratio of the intensity to the initial intensity is 1/2. This can be solved to determine the half-life, which is the ln of 2 over your rate constant. The last value we looked at was the lifetime of the triplet state, which occurs when the same ratio is equal to e to the -1, and is determined to be 1 over the rate constant. These are the resultant graphs from excluding the areas of the graph where the intensity was not changing over time. As you can see, the slopes are negative, which is expected for these trends, since the rate constant was negative. The slope of the naphthalene is steeper than deuterated naphthalene, despite how the graphs look. That is just because of the scaling. The steepness of the slopes results from the different values for the rate constant these two molecules have, where naphthalene is greater, as you can see by the slope. Solving for these values mentioned earlier is shown for deuterated naphthalene, resulting in a constant of 0.04565 seconds to the -1, or hertz, a lifetime of 21.91 seconds, and a half-life of 15.18 seconds. Comparatively, naphthalene has a rate constant of 0.1259 hertz, or seconds to the -1, a lifetime of 7.940 seconds, and a half-life of 5.504 seconds. And here is shown the equations used to propagate error for both of these values. So why is triplet decay a first-order reaction? In this case, decay of naphthalene, there's only one, it can only be one reactant. And this is true for any triplet decay because there's only ever one reactant involved since it's solely within the molecule or atom itself. How are triplet states formed? Triplet states are formed through the intersystem crossing between the first excited state and the vibrational excited state of the triplet state. This is a forbidden transition due to the spin of the electron flipping to become parallel to the electron in the ground state. This increases the lifetime of the triplet state since the electron has to flip back to antiparallel before returning to the ground state. Deuterated naphthalene has a longer lifetime and intensity than naphthalene due to the heavy atom effect. The heavy atom effect is the disturbance of spin-orbit coupling in a molecule due to atoms of larger mass. This causes an increase in the number of electrons in the triplet state due to an increase in the probability of intersystem crossing occurring. This increases the lifetime and intensity of the triplet state since more atoms are in the triplet state, causing a higher intensity and longer lifetime, since the decay of the electrons to a ratio of e to the -1 being longer. So comparing deuterated naphthalene to naphthalene, you see that the difference is being in the deuterium and hydrogen. Deuterium is 2 times heavier than hydrogen, where it would have a greater heavy atom effect, which would, of course, increase the lifetime and intensity of the triplet state, which is why deuterated naphthalene has a longer triplet state lifetime and intensity than naphthalene. So, going back to our hypotheses, which are these, the lifetime of the triplet state of deuterated naphthalene will be longer than protein naphthalene due to the heavy atom effect. And this was true. We saw that the lifetime of the deuterated naphthalene was longer. For the second one, the intensity of protein naphthalene would be much lower than deuterated naphthalene due to the heavy atom effect. And if we look at our two spectra, with the two decent ones, we can see that the intensity is much greater for deuterated naphthalene than it is for naphthalene. So both hypotheses were true.